All right, this video is going to look at approximating a tangent line. And to do that, we're going to have the equation of a tangent line at a point C, f of c, we know is y minus f of c equals f prime of c times x minus c. And again, we're just simply using the point slope formula. So this is y minus y1 equals your slope times x minus x sub 1. So we know this is our point slope formula to find the equation of our line at some point C, f of c. And the example we're given here is we want to find the tangent line approximation t, okay, the tangent line approximation t to the graph of our function f at the given point. So our function is 6 over x squared, and our given point is 2 3/2. So they want us to find the equation of the tangent line at this point. And to do that, we know that we need to find the slope of the line. Then we can use this point and the formula up here above to find the equation. So first, if we have our function f of x, we could rewrite this as 6x to the negative 2, and then we could easily take the derivative to find our slope. So that would be a negative 12x to the negative 3. So if we rewrite this, we could write this as f prime of x equals a negative 12 over x cubed. So there's the derivative. And we want to find the tangent line at the point 2 3/2. So to do that, we're going to use our formula up here. So we would have y minus y1, so that's y minus 3/2 equals our slope. So what is our slope? Well, at this point, our slope, we need to plug in here. We would have negative 12 over x cubed, so that's negative 12 over 2 cubed. Okay, so that would be a negative 12 over 2 cubed, which would be 8, times x minus x minus x1, so that's 2. And then if we simplify this, we would have negative 12h, well, that's going to reduce to a negative 3/2. And if we distribute that, we'd get negative 3/2 x. Negative and negative makes it a positive. The 2's would cancel, so that would just be plus 3. So we would then have y equals negative 3/2 x. And if we add the 3/2 over, that would become a positive 3 plus 3/2 would be 9/2. So this here is our equation for the tangent line. So we could think this is our t of x. That just stands for the tangent line at the point. So it would simply be negative 3/2 x plus 9/2. So there's the equation. And if we look at this graphically, you could simply go to your calculator, and I've already typed this in. Our function 6 over x squared is here, and I've set my screen from negative 3 to 3 on the x and negative 3 to 3 on the y. And you can see that our tangent line is drawn here as well. And we can see that here, this is our t of x, and all I did was type in negative 3/2 x plus 9/2, and that gave us this tangent line. So y1, I typed in the original function 6 over x squared, and then on the calculator under y2 I typed in this tangent line, and we can see here at 2 here's our point. So there's our point we're looking at the point 2, and then 1.5. You can see that that's over here. We have 1.5. So there's our point. And that's all that we need to find. And this is similar to what we've done before. We want to simply find the equation of your tangent line. So you take the slope, and there's our tangent line at that point. Now, I want to go a step further with this problem to kind of lead into the next video, which will talk about differentials. And if we go down here and complete this table, and keep in mind here our function, as we complete the table, the original function was 6 over x squared, and then the tangent line that we found at the point 2, 3. Now remember, our point was 2, 3/2. So the tangent line we came up with was negative 3/2 x plus 9/2. So we want to use those to fill in our table. And if you go to your table function on your calculator, you could quickly do this. So if we plug in 1.9, then the original function, we're going to get 1.6620. And if you plug in 1.99, we're going to get 1.5151. And at 2, we get 1.5. And then if we go a little bit greater than 2, we get 2.01. And you're going to end up with 1.4851, and then 2.1, we get 1.3605. Now, what we're looking at is this linear tangent line, this linear approximation is we want to approximate the value at this point of x equals 2. Well, if we do that, how close of an approximation is this tangent line to the graph? Well, you're going to notice at 2, if we plug 2 into t of x, we end up with 1.5. So notice here, f of x, the y value, when x is 2, the y value for both of these, for the original function f of x and then our tangent line, both of them are equal to 1.5 because that's where they intersect or they touch each other at x equals 2. Now we want to find out what happens though if we go a little bit smaller than 2 at 1.99. How close is the approximation? Well, it turns out to be if we plug 1.99 into t of x, we get 1.515. And if you compare the two answers here for f of x and t of x, they are still very close. And again, we're looking at a small change from 1.99 to 2. Okay, this would be your x plus delta x, and in this case it would be x plus a negative 0.01. So that's the difference here between the 2 and the 1.99. So 1.99 minus 2, the change in our x is 0.01. So that's a really small change, and even with that small of a change, our f of x and t of x is very close. So in other words, our tangent line is approximating the function pretty closely. And even if we go out to 1.9, we get 1.65. So once again, here we're accurate out to at least one decimal place. 1.6620 is the original function. Our approximation with the tangent line is 1.65. Now if we go above 2, we're going to see something very similar. If we plug in 2.01, we get 1.485, and for 2.1 we get 1.35. So what this is telling us, looking at the table, if we are close to where x is equal to 2, if we're close at this point, whether we go a little bit to the left or a little bit to the right, then this tangent line is going to be an approximation to this curve. Now, from looking at the graph, we can really tell the further we get away, for example, if we go out here to 1, if we look at the tangent line when x is 1, we have a point here, and then there's a big space here between the graphs. So the further we get away from this point, the less accurate the approximation for this tangent line to the graph. Clearly, as this gap up here at the top gets bigger, the approximation is not very good. But really with this approximation, we're looking at values that are very close, very, very small. So they're very close to where x is 2. So for example, we're looking at here, this change in the x is a negative 0.01. So what we're looking at is a very, very small value. So if I look at this change in x from here, the delta x is this negative 0.01. So here we have our 1.99. And again, from this approximation, then we can approximate here the y value to be 1.515. Now, over here we can see that delta x, we said is 1.99 minus 2. That's the change in our x, and we said the change in our x is very small. It's a negative 0.01. So if we want to calculate now from here, we want to calculate what is the change in our y value. So at this point, we're calculating what is the change in our y. Well, the change in our y value is going to be our function f evaluated at x plus delta x. So that's x plus the change in x minus f of x. So for us, that would be f of 2, and because it's negative, it's 2 minus 0.01 minus f of 2. And if we plug f of 1.99 into the function and f of 2 into the function from our table up here, we can see that we're going to get the 1.5151 minus 1.5. And if we subtract, that tells us that our delta y, the change in our y value, is 0.0151. Now what this is leading into is a way that we can easily approximate this change in y. Now, we know that delta x here, we're going to talk more about this in detail in the next video, but delta x is going to be equal to dx. This is our differential dx. And if you look at up here, clearly the change in x is going to be the same thing as our dx, because that's pretty much given to us here. But what we want to look at is how can we approximate this delta y, the change in our y value. And we're going to do that with our differential dy. Well, we know that y is equal to f of x. So if we take the derivative, that would be dy over dx. So the derivative of y with respect to x is equal to f prime of x. Well, if we think of taking this dx and multiplying it on both sides, we would end up with f prime of x times dx. And this here is our differential of y. This is finding an approximation of the change in our y. So here, if we substitute into this differential dy is equal to f prime of x. Well, the value we were looking at was 2, so we want to look at this evaluated at f prime of 2, and then we're going to multiply this by dx, and dx is equal to, we said the change in our x is negative 0.01. So then this differential dy is f prime of 2. Well, our derivative, if we go back up here, our derivative is negative 12 over x cubed. So that would be negative 12 over x cubed, and we're going to evaluate that at 2, so 2 cubed, which would be 8, and then we're going to multiply that by the negative 0.01. And if we simplify this out, then our dy is going to be equal to 0.015. Now, if we compare this, isn't that very close to the actual change in y, which is 0.0151? So what we're going to find out is this differential dy is going to be a way that we can approximate the actual change in our y. And again, this is going to kind of lead into the next video talking about these differentials. So what we're going to find out is our delta x is equal to dx, our differential dx, and we want to be able to find this dy, the differential of dy is going to be a very good approximation for the actual change in y. And keep in mind, when we're looking at these values here of this differential dy, or the change in y, or delta x and dx, keep in mind that these are very small changes. So you can see here we're looking at like negative 0.01, or values that are even smaller in that change. So once again, with this, we're trying to come up with a linear approximation. This is our tangent line here, and from that we can approximate values that are close to this point that was given of 2 and then 3/2. So as we're very close to this point with a very small change in x, we can use that to approximate values using the tangent line as opposed to the function.